And so basically, U substitution is kind of like the chain rule for differentiation when we take the derivative, right? It's like comparable to the chain rule, okay, but backwards. So this is essentially the chain rule, but backwards.
Like right after school.
Bless you. Okay. So we'll do the theorem here, which again, I know it's like very mathy and sometimes hard to follow, but we'll still do it just because it can be helpful. So let G and F be functions that are continuous and not differentiable. Oh yeah, and differentiable on I. Sorry, and differentiable on I, which is just an interval. Okay. If capital F is an antiderivative, notice not the antiderivative, right? An antiderivative, because you can talk about the plus c's being different values and stuff like that. So if capital F is an antiderivative of little f on the interval I, then okay, the integral of f of g of x times g prime of x dx equals capital F of g of x plus c.
Makes sense.
All right, so let me just show you kind of like, rather than having all these like funky, things right here, let me show you kind of an example of what I mean by that. So, for example, if we had a function sine of x squared like this. Okay, let's just say there was that. We take the derivative of this, right? We know how to take the derivative of this. Y prime would be, what's the derivative of sine? Cosine of x squared times 2x, right? Okay. So now, imagine integrating this derivative, right? So we take cosine and we integrate cosine of x squared times 2x dx. What do we know we have to end up with? It should give us sine of x squared, right? Well, look at what we have here. That's what we basically see right here, okay? We see a function, cosine, and inside that function is x squared. Right? So cosine's like the lowercase f, and then x squared's like the lowercase g. Okay? It's getting, I have a question? Oh, I'm sorry. See it okay there, James? Okay, thank you. Okay. So again, back to what I was saying there. Cosine is like the lowercase f, and then the function inside of that, the g of x, is x squared, times g prime of x, 2x, okay, right there, and that has to equal then capital F, which is the antiderivative of f. Well, what's the antiderivative of cosine? Sine, right? So it's sine of x squared. What's inside there? And I forgot the plus c. Okay, plus c.
Wouldn't that yield 2 sine x squared plus c? Because you're taking the, or no, times x, wouldn't it be x squared sine x squared because you take the antiderivative of the 2x?
No, because the idea. Oh, so first of all, you don't integrate. So you can't integrate over a product like that,
yeah.
right? If it was addition, if it was cosine x squared plus 2x, then yes, this would integrate to x squared. But then this wouldn't be able to integrate the way it needs to too. So the idea is that we basically have to have the perfectly set up chain rule to then integrate it to get back to the original function. Okay?
But what happens to 2x outside? Is it just assume that goes away?
This is the exact thing necessary to when we integrate it to get this. If we don't have the 2x, it is no longer this answer.
Yeah, that's just like the rule.
You need it set up that way.
So we have to memorize it.
Well,
we can't integrate it any other way.
you need, if you have a function within a function like this, so if you have cosine of x squared times 2x, this function inside the x squared, its derivative needs to be next to it there for us to be able to integrate it. Okay? That's the idea.
So it could be just as easy as like you saying f of x is blank, g of x is blank, and g prime x is blank, and then do that. It could be like tangent of square plus 2.
Integrate that? Yeah, so actually, and we would not be able to integrate that using U substitution. So while this expands our capabilities of integration, we still will come across problems that we are not able to integrate. So let me further with this a little bit. So in other words here, if U is equal to g of x, and here's where the U substitution part comes in. If U is equal to g of x, so U is the function kind of inside, okay, then du, the derivative of U, is equal to g prime of x dx, and the integral of f of u du is equal to capital F of u plus c. Okay? So we just do that little u substitution. We use a u instead of a g of x, and then du would be g prime of x dx, and so it ends up giving us something like this, which is much more familiar, right? We can integrate a lowercase function f, a lowercase f function to become a capital F function with the u substitution there. All right, and you'll see how, yeah, exactly. Some of you guys are thinking right now, F you, Mr. Whitford, trying to make us figure this out. All right. Forget you. All right, so anyway, nice. We're gonna do some nice u substitutions right now.
Why, do they get really hard or something?
They get trickier, yeah.
Nice.
But we're gonna take some baby steps here.
We're gonna take u substitutions later.
Yeah. I think they call them, I call them, well actually we'll do some not so nice ones here in a little bit.
Thanks, Lloyd.
Okay. So we'll start with nice ones first. So, nice! And the directions here are to integrate. Okay, so, let's go here. Letter A. Integrate 2x times x squared plus 1 to the 4th dx. Okay, so we'll integrate this. Could we integrate this problem prior to today?
No way.
Yeah. That was
Yes, we could. Okay, yes. Before U substitution, what could we have done here?
Multiply it all out.
Multiply it all out, get this gigantic polynomial, and then integrate all the pieces. All right, you guys want to do that?
Yeah.
No, let's use U substitution to help us. Okay, so to kind of go about U substitution here, we have to figure out, right, this U that we're going to use, it's g of x, and notice g of x is like the function within something else. So in this integrand here, what is the thing inside something else? The x squared plus 1. The x squared plus 1 is being raised to the 4th power. It's inside that 4th power there. So it's something, it's a function being raised to the 4th power there. So this is our u. So we're going to say, and this is important, you need to say let u equals. Okay? If you just write u equals, you could potentially lose points because you're like coming up with this like imaginary u. Saying the let u is like you're indicating that we're coming up with this new variable here, and I am saying let's have u equal x squared plus 1. If you just like start throwing u's into your integrand without, setting this up, then you're going to potentially lose points because you're not showing correct things.
We use u just for the sake of it being easier to write than long.
Yeah, you could. Yeah, I mean, you could. Exactly right. We're going to use u. We're basically doing like a change of variables, is what this is sometimes called too. Okay. So great. Let's plug that in. So now I've got the integral of 2x. Sorry. What did I put a u there for? Sorry. The integral of 2x times u to the 4th dx. Okay. Have we ever integrated something that has two different variables in it?
No.
Yeah. No. So this is not helpful so far. We are not any better off. In fact, we're worse off because now we made it two different variables instead of just one. All right?
Good job.
We have one more step here. We're going to take care of the 2x and the dx by going back to our u here. We're going to take the derivative of both sides. This gives me du here. The derivative of u will just denote as du. And then what's the derivative of x squared plus 1? 2x, and we're going to put a little dx here. 2x dx. Now you'll notice, 2x dx, we have that exact thing here in our integrand. And that's what makes this a nice u substitution. Sometimes we have to manipulate this around. But since we have the exact 2x dx, instead of writing 2x dx, what can I write? Du. And so this becomes now the integral of u to the 4th du. So what was going to be like ridiculously long and hard because of having to expand it out and then making sure we don't make any mistakes there, now it's just a matter of integrating u to the 4th.
Why did the 2x dx just go away?
It didn't go away, we did a substitution. Notice what replaced it, the du. What do we say du is equal to? 2x dx.
Oh, okay.
So it's a substitution.
That just becomes 1/5.
So right, it becomes 1/5 u to the 5th plus c. But what's u?
X squared plus 1.
X squared plus 1. So then the final answer is 1/5 x squared plus 1 to the 5th plus c. And there it is integrated. It's pretty slick. Question.
So when we integrate u, we aren't integrating relative to like a variable. Like it's not really du over dx. It's just we just note it as du, just for our sakes of getting the problem.
So, like right here, you're saying?
Yeah.
So I'm skipping a little step here. So Austin's question here, and I just want to point this out. So it's a good question. All right. So technically, I'm skipping an intermediate step here because you'll see. So what we're going to do, what I'm technically doing here is taking the derivative of both sides with respect to x. The derivative of u with respect to x is, so I really should go like down here. So it's going to be du dx equals then 2x, right? But again, I have 2x dx I have to deal with here, so I'm going to multiply the dx over, it ends up being du equals 2x dx, and then I can do the
So
substitution.
you always do that.
That's exactly. So I just skip that step because it's like, we don't need to see that. But yeah, that's what's going on there. So good question. Yeah.
I get all the parts of all the substitutions, but can you go like, I guess from the second step down, like slowly again?
Right down through here.
Yeah.
So I mean, at this point, you want to you ignore everything else and just like how do you integrate a variable to the 4th power with respect to that variable? That's all it is. Yeah, it's 1/5 u to the 5th. It's the power rule. Just like if it was integral of x to the 4th dx, it would be 1/5 x to the 5th plus c. That's all there is to it. It's very nice. All right, let's look at another one here. Same directions. We're going to integrate here. All right, let's say secant squared of x times tangent of x plus 3 dx. Okay, now, what should u be here? Okay, yeah, it should be tangent of x plus 3. All right, now you might think to yourself, u could be secant of x though, Mr. Whitmire. You just went over here and you said, okay, we're going to pick the function that's inside of another function. Well, here x squared plus 1 was being raised to the 4th power, so we chose x squared plus 1. We could choose secant of x to be u. So let's just hypothetically, I'm going to do that here, let's let u equal that secant of x. Because it's being squared, right? It's inside the square. So it's secant of x, that quantity, squared. So let's let u be secant of x. If I let u be secant of x, what's du then? What's the derivative of secant x?
Secant x tangent x.
Secant x, tangent x. Do you see the problem with selecting secant of x to be our u here? Do we have a secant x, tangent x hanging around in here?
No.
Not really, no.
We have to make a secant times secant.
If we spread it out, but then we still have the plus 3 secant squared, although, actually, now that I'm looking at that, it could potentially work that way, now that I'm looking at it. It could potentially
So is
work.
that like a judgment call you have to make of what you want to assign you to in a problem?
Sometimes you have a little bit of choice, yes, but yeah, but it does work actually in this case if we manipulate things around a little
Yeah,
bit.
because you have to take out this, you have to make secant times secant, and then distribute it to the...
Yeah. Let's let u equal though, like Jack was saying, tangent x plus 3. Okay, so did I lose you?
Yeah, I'm lost.
do it myself.
Oh, okay.
I'm lost. Yeah.
All right. Let me get to you. Tyler, what is your question?
You mostly just want to plug in the thing that has the most components in it.
Kind of.
Is that like a general rule?
Really what you want to pick the u such that whatever's left over is the derivative of that u. That's what you really want to be your guideline here, okay?
Whatever's left over.
Whatever is, so you pick your u such that the derivative of that thing is what the
So,
rest
yeah,
of the
yeah,
integrand
the
is.
derivative of tangent.
So, right, so Jack chose tangent x plus 3 because its derivative tangent is
Yeah.
secant squared. And then the 3 is gone, dx. And so there, that takes care of it. And so what does this become? It becomes the integral of u du.
Yeah, I got there. And I was like,
Sounds like tuna.
Does.
Like fish.
Okay?
You just walked in.
It could be the drink. Maybe it's the drink. It just has like a smell to it.
Sounds like tuna.
Yeah.
Why, we were not supposed to go to sheep after we came back from the middle school. Lyle,
So.
what are you doing?
Didn't you go to shoot?
Okay, back on track here, folks. Integral of u. So Joey, what's it's u to the what here?
it's you to the 1?
1. So what's the integral of u to the 1?
Oh, so it'd be u to the 2.
Yeah, u to the 2, and then 1/2 out front plus c.
It's 1/2 of the greatest band plus...
All right, u2. I like u2 as well. Tangent of x, and you plug in for your u, and then there's the final answer. Okay? And you don't have to square that out if you don't want to. I mean, that's fine.
All right, can you give us one
Say
more?
again?
Having a C is okay with these problems, like you don't need to...
Yes. The C for this will be different than the C for that one. There'll be different C's potentially. So, actually, no, they should be the same C. Never mind. But how you get them will be different. Yeah. Yes, question?
Do you have a rubber band?
I do, but I'll get you one later, not right now. All right, I want you guys to try 2 then. Here you go. Try integral of 3e to the 3x dx and the integral of 5 cosine of 5x dx. Okay, try and integrate those. And Maya, I can, let's see here. Yeah, you want me to try and work with you here some since. Let me just freeze it, hang on, and then I can leave that up there and I can get you.
Okay, so,
In my head.
so we're talking about integrating by substitution today, which is sometimes just sort of to use substitution. So it's like basically another tool that we're going to have to allow us to integrate things that we couldn't integrate before. We still will be able to, we'll still run across things that we don't know how to integrate because, you know, it just, there's some things we still can't do. But, I mean, we're not gonna at least have more things to integrate now, okay? So, it's basically, what it ends up being, it's basically like the chain rule but backwards. Okay, so what I mean by that, for example, is like, you know, when you have a function here, sine of x squared, and you take the derivative of that, you have to use the chain rule, right?
Yeah, I guess you could just make it 3.
Sine is cosine, leave what's inside, times the
No,
derivative.
that wouldn't work.
So since this is the derivative of y, of this, that means if I integrate this, I should end up with this. Right? Okay? And so that's the basic idea here. So if you look, you've got, and this is more generally stated, you have a function within a function, so indicating like the chain rule there, and then you have that inner function's derivative on the outside. Just like here. There's x squared inside cosine, and we have the derivative of that x squared right there, the 2x on the outside. You see that? Yeah? Okay, so I'm sorry. Integrate that, right? Integrate that, and it takes you back to the integral of lowercase f, capital F, so it just integrates the cosine to sine, because the integral of cosine to sine. The g of x stays in there still x squared. Notice the g prime of x, though, disappears, and then you love c. Okay, now, that right now is like magic to you right now, but you'll see it in practice here, and that's okay. So here's where the substitution part comes in. We use the letter u to replace g of x. And then if we take the derivative of both sides there, we end up with du is equal to g prime of x dx. okay, right? The derivative of u is just du. It's really du over dx, but then we just multiply the dx over to get there. And then we end up with this then. The integral of f of u du is equal to the capital F of u plus c. So let me show it to you in practice here, okay? So here, prime example, okay? To choose our u, we normally take the u to be it's inside of something. So here in this case, x squared plus 1 is inside being raised to the 4th power. So we'll let u equal that x squared plus 1.
Well, it has to equal
Okay.
e to the 3x.
So we take, so we basically have this substitution right now. I replace x squared plus 1 with u. But now if I go to try and integrate this, I have x's goes together with u's, and we never integrate anything like mixed variables like that. So I need to take care of this 2x and dx. Well, if I let u equal x squared plus 1, then the derivative of u is equal to 2x, I think, dx. So look at that though, 2x dx, that's exactly what we have.
Oh, I see what you did.
So the 2x and dx can be replaced
What?
by this du. And now look at that, it's integrating u to the 4th with respect to u. That's easy, it's 1/5 u to the 5th plus c. And now I can replace the u with x squared plus 1, and then there's my final answer back in terms of that. Make sense? So here, similar kind of idea, you have some options. I mean, like, in general, it's like hard to, like, right now, like, picking your u is going to be, like, figuring out what is the u and what is not the u is going to be a little bit tricky, right? You have to pick that out. The basic kind of, like, idea is you want to choose the u in here such that its derivative will take care of the rest of the thing, the rest of the problem. So, for example, here, Jack was able to identify that this tangent x plus 3 is the u. Was he not the one that did it?
No, that was me. He was.
Oh, okay.
Jack.
Oh, sorry. So Jack was able to correctly identify that tangent x plus 3
no,
is the u here. And
No, wait.
he can see that's the case because we let that du, then our du is secant squared x dx, which is what's left over there too. See what I'm saying? So we end up with this u, and then those two pieces are du, so it's u du. So the integral of u is 1/2 u squared plus c. Plug back in the tangent x plus 3 for the u. That's your final answer. Mathematics. Okay. So we're going to go over these next two now.
Okay, let's take a look at these next two. All right, what is our u?
E to the 3x.
E to the 3x, okay? Let's let u equal e to the 3x. So that means if I just write it with just u here, then it's going to be integral of 3u dx. Okay, and then let's see here. Ooh, okay, we have some trouble. We can pull the 3 out front. But can we integrate u with respect to x? We need to deal with this dx. So that means we should probably take the derivative here, both sides, right? We get du equals, what's the derivative of e to the 3x? 3e to the 3x dx. And now we have some problems because we have dx, but we have a 3, but we do not have an e to the 3x to substitute in the du there. So so the 3 and the dx match up with the 3 and the dx here, but we don't have an e to the 3x to complete the substitution. So we can't plug in a du here.
You plug in u first?
You need to let u equals 3x.
So, yeah, we chose our u poorly. That's okay. That's going to happen. This is part of the process of how you learn how to do
I
these.
got my answer then.
How do you know?
You see why it doesn't work. That's very important to see that it does not work.
I need to look at a problem and be like, oh, that's the
You will develop an intuition as you go and make mistakes. At the start, you will have to choose, and sometimes, as you know, the knight at the end of Temple of Doom said, you will choose poorly, and then you turn into a skeleton and you die, and it's like you melt and turn into dust and blow away. Alternatively, you want to choose wisely, okay? Like Indiana Jones did. He chose the cup of a carpenter, and he chose wisely, and he didn't die. So anyway. Okay, the least flashy cup, exactly right. You know what I'm talking about. Okay, so we're going to let u equal what? 3x. du is then what? 3 dx. Now let's look at that substitution. That's now the integral of e to the u, but the 3 dx It's still there, but that's what our du is, so it exactly substitutes like we needed to. It's integral of e to the u du. And what's the integral of e to the u with respect to u? E to the u plus c. Not times u prime, just plus c. Okay? And then we're plug in the u, and there it is, e to the 3x plus c.
How do you make u equals 3x versus 3x? Oh, that's 3x.
It's inside, isn't it? It's inside something. Typically, we pick something that's inside something else. So it's an inner function there. Okay. So going by that same Donovan question and then Trinity question, or no? Okay, Donovan. Say that one more time. I'm sorry. The derivative of e to the u is e to the u. Yep. So the integral of e to the u would be e to the u as well. Again, you got to think of it as a variable here. I know it's equal to a function, but you are treating it as a variable, like it's just an x or like something like that. Okay. So with that idea in mind here, what should our u be for the second one? 5x. Okay. Let's let u equal 5x. It's okay if you guys make mistakes on these two. That's how you're going to develop your sense of how these work and what you're supposed to choose for the u. Okay. Say again? Why u is the letter? I mean, I'm sure there is. I'm assuming the person that maybe came up with this technique way back, when, they probably used a u at the first place. You know, it's like, why do we use x's as our common variable? Who knows? I mean, it's kind of a dumb one, actually, because you have, like, multiplication symbol, which is an x too. That gets confusing. Who knows? Yeah, exactly. So, anyway, let's rewrite this. Could use z, but that looks like a 2 sometimes. So anyway, cosine of 5x. So what does this become then if I use this substitution? Not 5 cosine u. Nope. Cosine u du. Oh, I see. You're going to say 5 cosine u dx and then do the substitution. Yeah, okay, sorry. Gotcha. Integral of cosine? Yep. Sine of u plus c, and we resubstitute the 5x. And there it is. You can convince yourself you're right by taking the derivative of your answer, right? You can convince yourself you're right by taking the derivative of this, and it should match back up to that. You should never know whether your integral is correct or not. Or you should never be unsure whether your integral is correct or not. You take the derivative of it, and you should get back to your integrand there. Okay? There should never be a question in your mind. All right, 2 more here, and I'll give you guys your assignment. Dos más.
What does mas mean?
More?
Yeah, that's what I was thinking about that. I was like, what does that mean? Oh, no.
Every time I think of Taco Bell, I think about that drunk guy telling me that there was a car show outside.
Were you there when that
really just
supposed veteran was like, I've seen B-52s working? Were you there for that? No? Oh.
Sorry, I'm switching back to black. I meant to do that. Okay, anyway.
Not so nice.
Not so nice.
Okay, Ryan.
I'm allergic to cats.
Okay, here we go, folks.
Notes match your shirt.
That's right.
Shirt like comment.
Is that a Q?
Squared. Those. All right. Do we need U substitution to do this problem? No. Okay, so we do not need U substitution here. What could we do to solve this problem?
Multiply.
Boil it out, multiply through the x, get that polynomial, and integrate it. In fact, this one's very doable. It wouldn't be that bad at all. Okay? Let's see here. This one right here, do we need U substitution to do this one?
No.
This previous one?
No.
Yeah, we do. There's no way to integrate cosine of 5x really without using that U substitution. We can't like manipulate it around. We can't simplify it at all. Same thing here for the e to the 3x. There's no real way to like manipulate this around to get something we can integrate. We have to use U substitution here. Same thing for the other previous trig one as well. But these polynomial ones, we could just multiply it all out and get the answer that way. But let's practice our U substitution
You'll ask
here.
us like using U substitution and do this.
No, I'll just say integrate, and you'll have to be able to determine whether you need to use U substitution or not. And the problem is that now that I'm showing all these U substitution problems, you guys are going to now have difficulty with the easier ones that did not require U substitution. I'm going to give you something like, 2 cosine x, and you're like, I don't know what my u should be. It's like, well, there's no u that you need when you're integrating 2 cosine x.
U or the U?
So you're going to want to apply it all the time. U substitution does not apply all the time, okay? So let me just say that, and then you'll still have questions later. That's okay. Okay, let u equal, what should it be here? Okay, let's try x squared minus 1 and see what happens.
Yeah, I think it's not supposed to be x squared minus 1. I should say that.
I just...
It works.
Okay, what is, so let's do that. So what's du then? 2x dx. Now,
When you du equal 2x.
we do not have 2x dx. What do we have?
X.
We have x dx. So, how can I manipulate this, though, to get x? It's an equation. How can I manipulate this to get x dx?
Du over 2.
Divide both sides by 2. So I'm going to make it 1/2 rather than divide. I'm going to multiply both sides by 1/2. Yeah, make it 1/2 du equals x dx.
So what does that mean, Mr. Will?
So when I substitute, when I replace x dx, what does x dx get replaced with? 1/2 du. Now I'm going to write this in a strange way because this is what makes the most sense. But later, well, anyway. All right, so let's rewrite our integral then. X squared minus 1 squared becomes what?
U.
U squared. The x dx becomes 1/2 du. Okay, kind of like,
We have a lot of U's.
When you integrate, is it like 1/2 just like a constant? You
yes,
use it away?
1/2, okay, is just a coefficient. So where can I pull that 1/2?
Front.
Out front. That's it. Okay, and now we can integrate that, no problem, right? What's the integral of u squared? 1/3 u cubed. Don't forget there's the 1/2 though, right out front. There's this 1/2 times 1/3 u cubed plus c.
But
Bro,
that,
I totally just did
wait, what, that doesn't, but that,
What's the matter?
What was that, Ryan?
Now the 1/2 distributes.
oh,
Okay, 1/2 times 1/3 gives us 1/6 u cubed, but I'm going to rewrite that as x squared minus 1 cubed plus, and then I could write 1/2 c, but
It's just c.
it's a constant. So distributing the 1/2 to the c doesn't really matter. Okay, so you can just leave it as c still. You don't have to put the 1/2 there. But there's the answer. That's it.
Ta-da.
Ta-da.
But if you were, it was like a problem where we know at some value it equals something, then c being over 2 would be important, like you're finding c.
No, it would not be. So, guys, Christian's question is very important here to show. So, Christian was saying, all right, so Mr. Wood, let's say we did put the 1/2 in front there, okay? If you were doing a problem where we found the c value, let's say this was a velocity and we were integrating to get a position, and then I wanted you to find the actual position function, that is, find the c value, okay? If Christian chooses to leave it 1/2 c, then the c value that he solves for will be different than the c value that Austin might solve for if he doesn't have the 1/2 there. But they will end up being equivalent. So let's say the c value for Austin will be 3, your c value will end up being 6 if you leave the 1/2 out like that. In other words, it'll simplify to what his is if you do the 1/2 times your c value.
Okay.
You see what I'm saying?
Yeah.
So, in other words, it won't matter. His c will just adjust depending on the fact that he absorbed the 1/2 into the c. Your c value will be different than his because you left the 1/2 out. In other words, it won't matter. It'll be the same thing. It'll be equivalent.
So I don't know how complex we're gonna end up getting with the, use of the picture.
Okay.
If you were to ever have, like, the exact one be u prime plus 1/2 du, like, if there was just a plus 1/2, you could not have pulled out the 1/2, right?
Yeah, correct, because it's plus. Yeah, but it's always going to be a product. It should always be a product. So, all right, 7 secant of 4 theta, tangent of 4 theta, d theta. That's our last one here, and I'll get you guys started on the assignment. You're welcome. Okay, so there's our setup. What should we let u equal? So you want, okay, so Yeah, so what do we want let u equal what?
4 theta.
Let u equal 4 theta. Let's try that. Okay, because the 4 theta is again inside secant tangent there. Alright, so if u is 4 theta, that means du is what? 4,
Or d theta.
yeah, d theta in this case, right, d theta.
So that
Okay.
over x.
Now, again, we don't have 4 d theta, we're going to have d theta and then a 7 here. Now the 7, what can I do with that?
Put it out front.
Yeah, we can pull that out front. So let's pull the 7 out front and make it just secant 4 theta, tangent 4 theta, d theta. Okay. So far so good. And let's do one more step here. Again, you don't have to do this, but I'm just going to show it just to kind of make it more obvious. So we have secant u, tangent u, okay, but I still have this d theta we got to deal with. All right, we still have this d theta we got to deal with. So again, this is kind of a funky way to do it, but I'm going to try it this way and see what happens. Okay, so we got to deal with this d theta. D theta, what's that equal to? Well,
du over 4.
yeah, we have to get that 4 over to here, so we're going to make it 1/4
Wait, where the
du.
Wait, why is du equals 4 theta? Where'd the 4 come from?
U equals 4 theta.
Yeah.
The derivative of u is du. The derivative of 4 theta is 4 d theta. And again, if that's uncomfortable, Ryan, what's really going on here, like I said, the intermediate step is it's really du d theta equals 4, and then we multiply the d theta back over. So the 1/4, I'm not even going to bother writing it in the integrand. It's a coefficient. I'm just going to pull it out front and make this 7/4.
That's what I did.
Integral secant u, tangent u, du. Okay, now everything's in terms of u. We can finally integrate. Now, this is why it's so important to know your integral rules here, because some of you guys might have looked at this and said, wait a minute, Mr. Wade, it's okay to just leave a secant and a tangent in there? Yes, because what's the integral of secant u, tangent u?
Negative secant squared of x. Or no, it's just secant squared.
It's just secant. 7/4 secant u plus c. Okay? That's why it's so important to know those integral rules. And so then we resubstitute back secant of 4 theta. There it is. Totally good. Okay?
I like it.
Pen is running out of ink and
Yeah, so I'm buying the retractable one.
it's not.
Look
It's not even out of ink.
Mine is like halfway done and it's still writable, but then I have ones that are completely full and just dry. And I didn't even leave them on tabs.
So there it is. Questions on any of that?
Careful to print it.
I'm going to give you guys your assignment then, okay?
Barely
So
know.
it's out of the book.